What if your diet was as unique as your fingerprint, tailored perfectly to how your own body responds to every single meal? Well, this is the core idea behind precision nutrition. It all starts with moving beyond some of the outdated health metrics we've used for decades. So, we're going to look at how deep phenotyping and machine learning are making this a reality by predicting our body's unique responses to food. Here's what we'll be covering. First, we'll talk about the limitations of traditional health assessments. Then, we'll get into the advanced techniques, giving us a much clearer picture of our bodies. From there, we'll look at the data, see how machine learning gets used for prediction, and finally, we'll discuss what this all means for the future of personalized health. So, to start, what's the issue with how we often measure health right now? A great place to begin is with a metric nearly everyone has heard of: body mass index, or BMI. Now, BMI is used everywhere in public health, but it has a fundamental flaw. It can be quite misleading when you're trying to figure out an individual's metabolic health. Think of it this way: a professional athlete and the sedentary person could have the exact same BMI, but their health profiles are worlds apart. Why? Because BMI is simply a ratio of weight to height. It has no way of telling the difference between dense, heavy muscle and unhealthy body fat. This leads to some serious misclassifications. Okay, so if BMI isn't giving us the complete picture, what's the alternative? The answer is something called advanced phenotyping, which gives us a much more granular, high definition view of our physiology. To get this detailed picture, scientists have a whole toolkit. For instance, DXA scans give us a breakdown of body composition: how much is bone, lean tissue, and fat. Other tools like CT and MRI scans let us see exactly where the fat is stored, which turns out to be crucial for understanding metabolic risk. And newer tech like 3D body imaging helps us identify different body shape archetypes. And where we store fat matters a whole lot. It seems not all fat is created equal. Android obesity, when someone carries fat around the abdomen, think of the ab shape, is strongly connected to a higher risk for conditions like type 2 diabetes. On the other hand, thyroid obesity, where fat is stored more in the hips and thighs, doesn't carry the same level of metabolic risk. The real problem maker here is visceral fat. This is the fat deep inside your abdomen, wrapped around your organs. You can't see it or pinch it, and it's not dormant, it's metabolically active. It releases inflammatory signals, which can cause low-grade inflammation throughout your body, contributing to a number of chronic diseases. So we've gathered all this incredibly detailed data. What's next? The next step is turning all that raw information into something we can use to make predictions. This is where the data modeling pipeline comes into play. The primary goal of these models is to predict how your body will react to a meal. We measure this reaction with a metric called the incremental area under the curve, or IAUC. You can think of it as a way to quantify the spike in something like blood sugar after you eat. The better we can predict that spike, the better our nutritional advice becomes. This pipeline is a bit like a four-step recipe. First, you have the raw ingredients, all our deep phenotyping data. Then you prep those ingredients, cleaning and processing them. Next, and this is important, you select only the most relevant ingredients or features. And finally, you combine it all using machine learning to create the prediction. That third step, feature selection, is absolutely essential. With hundreds of data points for each person, we need a way to filter out the noise. Feature selection helps us identify the data points which are most predictive, like visceral fat, for instance, and ignore the ones which aren't. This makes our models more accurate and more efficient. So in the final stage, we take these carefully chosen features and feed them into machine learning algorithms. This is how we build the actual predictive model. Two types of algorithms have been especially useful for this. Random forests are great because they can handle all the different kinds of data we're working with, from clinical measurements to survey responses. Then you have gradient-boosted regression, which has been a major step forward in allowing us to predict blood sugar responses with much greater accuracy than older methods. But there is a challenge here. These sophisticated models can sometimes act like a black box. We put the data in, we get a prediction out, but we don't always understand how the model made its decision. It's like a brilliant student who gets every answer right, but can't show you their work. To open up this black box, we use techniques like partial dependence plots. What these plots do is let us isolate a single factor, say dietary fiber intake, and see how changing it affects the model's prediction while everything else stays the same. It helps us understand the why behind what the model is telling us. This brings us to a really critical point. It is absolutely essential to understand the difference between a model which predicts an outcome and one which proves causation. This distinction is so important. A predictive model might show people who eat lots of fiber have better blood sugar control, but this is a correlation. It doesn't prove eating more fiber will cause your blood sugar control to improve. Causal inference is the much harder science of figuring out if A truly causes B. Prediction asks what will happen, while causal inference asks if I do this, how will it change what happens? We've covered a lot of ground here, from the problems with BMI all the way to the frontiers of machine learning. So let's quickly review the key takeaways. So, what are the big ideas to hold on to? First, to understand health, we need to look far beyond simple measures like BMI at things like visceral fat. Second, turning all this new data into useful predictions requires a methodical, multi stage pipeline. Third, we need tools to interpret what these complex models are doing. And finally, always remember prediction is not the same thing as causation. Okay, let's see what you've picked up. First question for you. Why is that deep, internal, visceral fat a more concerning indicator of metabolic risk than the subcutaneous fat right under your skin? Second question. In the data pipeline we discussed, what's the goal of a feature selection technique? Why do we mean to filter our data before we even start building a model? And one final question. How do we get around the black box problem to make sure we understand a model's predictions? What do you think the answers are? Leave your answers in the comments. And if you like this video, hit that like button. And please consider subscribing to my channel.